So let's continue talking about relationships between sets. Remember, we had said that the union symbol, which looks like a U, means the collection of all the elements that are in either one set or another. So F union G means all the elements that are in the set F or in the set D. So that's going to look like A, B, C, D, and E, right? We just squish those two sets together into one big set. Now the intersection symbol, which looks like an upside down U, means the set of elements that are in both F and G. So F intersect G is going to be the set of all elements that are in both F and in G. Well, let's see. It's not going to be A, because A is not in here. Not going to be B, it's not going to be C. It's actually not going to be anything, right? There's no elements in the intersection here. We could say that this intersection is equal to the empty set, because there's nothing that's in both of those sets. If we wanted to draw a Venn diagram of this, what's going to be in the overlap? Nothing, right? There's nothing that's in both of those sets. So their Venn diagram is really going to look more like this. Right? We've got A, B, and C, and then we've got D and E. They're separate. There's no intersection. And so two sets that have that property of having nothing in common are called disjoint. So we say two sets are disjoint if they have no elements in common, that is if their intersection is empty. So let's look at a few more examples to make sure we understand how these unions and intersection works when we're looking at infinite sets, right? Because so far we've only looked at finite sets, but we can extend this to the idea of infinite sets as well. So remember that this fancy n means natural numbers, the fancy z means the integers, and we're going to define a set m, which is going to be -1, -2, -3. So it's negative integers only, right? It's just the negative versions of the natural numbers. All right, so let's start with n intersects z, the natural numbers and the integers. So what elements are in both the set of natural numbers and also the set of the integers? Well, 1's a natural number and it's also an integer, so 1's in there. 2 is a natural number, it's also an integer, so 2's in there. Actually, every natural number is an integer because we said n was a subset of z. So you're going to end up getting the entire set n back. So notice that because the natural numbers was a subset of the integers, their intersection is just going to end up being that smaller set n. How about m and z? So m is the negative integers, and z is just all of the integers. Well, -1 is in this set m. It's also an integer, so it will be in the intersection. -2 was in both, -3 is in both, same thing. This set m happens to be a subset of the integers, so their intersection is just going to give you back that set m again. Now what about n and m, the set of natural numbers and the set of negative integers? Well, 1's an n, but it's not an m, right? -1's an m, but not an n. Actually, this set only contains positive numbers, and this set only contains negative numbers, which means this is the empty set, which means these two are disjoint. Right? They have no elements in common. All right, what about if we try to union these sets together? The natural numbers union with the integers, right? We're squishing everything together into one big set. So we'll get all those positive integers from n, and we're unioning that with z, which is positive numbers, negative numbers, positive integers, negative integers, and 0. Well, unioning them together isn't really giving you anything new here, right? By unioning in n, you're just putting in elements that are already there, which means you're just going to end up getting back out again this set of integers here. So n happened to be a subset of z. When we union these together, we got z. Similarly, m happens to be a subset of z. When we union them together, we're not getting anything new, right? -1, -2, -3, those were already members of z. So we get nothing new, so we get the integers again. What about the natural numbers unioned with the negative integers? Well, the natural numbers are going to give you 1, 2, 3, etc. And then m is going to give you -1, -2, -3, etc. So we end up with positive and -1, positive and -2, positive, -3, etc. Which is almost a set of integers, except not quite, right? Because technically we don't end up getting 0 when we union these two sets together. So it's not quite equal to the integers, but it's close. Okay, the last two relationships that we want to describe between sets is the idea of set difference. Now, in some sense, you can think about unioning two sets together as like adding them together, right? When we unioned the natural numbers and the negative integers, we sort of squished them together into one big set. It sort of feels like addition if you wanted to define addition on sets in some way. So what does subtraction look like? Well, we can't really subtract elements from a set that aren't there, but what we can do is have this idea of the difference between two sets. So the difference between A and B, which we denote using a subtraction symbol, A minus B, or sometimes a slash, A slash B, and that's going to be the set of elements that are in A but not in B. In other words, start with the set A and then take out any of those elements that happen to be in B. So let's look at this particular example. A is the set 1, 2, 3, 4, and 5. B is the set containing 3, 5, 6, and 7. So A minus B is just going to be the elements of A that are not in B. All right, well, that means 1 gets to stay because it's not in B. 2 gets to stay because it's not in B. But 3 we have to throw out, right? We're taking away all of the elements of B, so we're going to take this away, right? We're not going to include 3 here. 4 gets to stay because it's not in B. But 5 we sort of have to take it away as well because it's an element of B. And so we're left with 1, 2, 4. Now B has these extra elements 6 and 7, but they really don't come into play here when we're talking about this set difference. We really only want to take away the things that happen to be in both sets, right? The things that happen to be in the intersection. Okay. Similarly, if we wanted to look at the set B minus A, we start with B, and then we throw out any elements that also happen to be in A. So I have to throw out 3 and I have to throw out 5, since those are also elements of A, and I'm left with just 6 and 7. So notice we ended up with, if we looked at the Venn diagram of these two sets, or the same one we had in the last video, this Venn diagram looked like 1, 2, 3 was over here, 4 was here, 5 was here, and 6 and 7 were over here. So what is the set A minus B? It's exactly the elements of A that are not in B. So it's sort of this little half moon area. This is the set A minus B. It's the stuff in A that's not in B. And similarly, B minus A is going to be exactly the stuff that's over here in this other half moon area. The stuff that's in B that's not also in A. So this is just giving you a way of identifying the elements of a particular set that aren't in the intersection, right? We just took out 3 and 5 because those are in the intersection. So that's what we mean when we talk about the difference between two sets. And we can extend that idea to look at a set within a particular universe. Remember, we say that U is some universal set if some set just lies within it, right? If it's a subset of some larger set. So if U is some universal set, and A is a set that lives within that universe, then we can talk about the complement of A, which we denote A bar, right? A with a bar on top, or A raised to the C. You'll see this a lot in web work. You'll see this notation instead of A bar, but this is more common. And the complement of A is just everything in the universe except for the stuff that's in A. So you can think about the complement as being the difference between the universe and A. So it's everything in the universe that's not in A. So for example, using that same definitions of A and B that we saw up here, if the universal set is all of the natural numbers, then we can define A complement and B complement as just, well, A complement is going to be everything in the universe except for the stuff that's in A. So it's all the natural numbers except 1, 2, 3, 4, and 5. Okay, well that's going to give you 6, it's going to give you 7, it's going to give you 8, going to give you everything, right? All natural numbers except the first 5 of them. Similarly, if we wanted to define B complement, that's just going to be everything in the universe except for the stuff that's in B. Right? The universe is the natural numbers, and we want to take away the elements of B. Take away the elements 3, 5, 6, and 7. So what's going to be left? Well, 1 and 2, for instance, will be there. 3 is not there because 3 is in B. 4 is in the universe, 5's not there because 5's in B, 6 is not there, 7's not there, right? We're taking out the elements of B. So the next one would be 8, then 9, then 10, etc. What does this look like on a Venn diagram? Well, if our Venn diagram just has the set A in it, if it's just this one circle, then A complement is going to look like everything outside of that circle. Right, so if this is A, this shaded part here would be your A complement. And in a larger Venn diagram, like let's say we had both A and B here, this was your A and this was your B. Let's say I wanted to shade in B complement, this set here. Well, I would need to shade in everything that's not in B, everything outside of the B circle. So that's going to give you this part here, this little half moon, but it's also going to give you everything out in this little ambient space out here. Right? It's literally everything in the box except for the stuff that's in B. Right? So you can imagine that this gets a little bit more complicated if you're looking at, let's say, more than 2 sets. But you'll see some examples of those as in exercises.